Assalamu alaikum warahmatullahi ta'ala wabarakatuh. Ladies and gentlemen, welcome back to another live stream. Alright, let me share the stream with my Discord server. Please join my Discord server so you can get notified of new streams. Okay. Let's see. Alright, so we're gonna start, I think, in 5 minutes or so. So you can go straight forward into the minute 5 if it's not live, if you're watching after this live stream. So alright. Rust generic. So today we're going to be doing some Rust generics, of course. We're going to be creating a vector. Well, honestly, let me just keep it until the 5-minute mark. So if anyone has skipped already, they can get this information. All right. So we're going to be waiting for people to join in until the 5-minute mark, and then we can start pretty much. All right, pretty cool. Pretty cool. And by the way, I think we're going to start like a new project soon. Just going to be a little open source team project kind of. So if you're interested into that, then you could head into the technology channel, and there we're actually, just going through. And so at first we tried Zig, but it was just too much friction. So right now we're gonna be going with Rust, basically. So yeah. Alright, so let's just wait until the 5-minute mark and we can start. Okay. Okay, let's see. Well, 5 minutes is kind of too much. Oh well, anyways. Okay, 5 minutes in. Alright, I gave enough chance for anyone who wants to join. Alright, welcome Hats, how is it going? Welcome to the live stream. Welcome, how is it going? I'm the Geeko. Oh, I see, that's nice. Welcome to the stream. So I'm the Geeko is from one of the people that wanted to join in on this kind of little adventure. So it's like you can only go as much as a solo developer. So we're trying to make a little team, and just try to work on some projects, you know, some crazy projects, and just see how it goes. So there is the Geeko, who's actually right now at the stream in the stream, and there is Ibrahim. I'm not sure if it's his real name or not, but either way, he's also gonna be joining. Although Ibrahim doesn't really have any Rust knowledge, I think. So that's why I first wanted to go with Zig, but like, bro, it was too much friction. Too much friction. So and also the Geeko, he have a little bit, I think, of knowledge about Rust, but yeah, pretty much. Okay, so it's already the 5-minute mark, so let's get started. So basically we're going to be learning some Rust generic programming today, practically, of course, by implementing a Rust vector kind of class or struct. Let's see, it's going to be a generic vector, generic mathematical vector of dimension n, you know, and of scalar t or whatever. We'll see. So let me pop out the chat first. Please, if you have any questions whatsoever, let me know, because I really I can give you my best by answering your questions instead of just me rambling and trying to figure out what you don't understand and what you understand, you know. So please ask questions whenever you want. I'll try to explain them, or I try to answer them. Okay, so let's get started. So here I just have a simple library. Basically, it's have some tests here, and yeah, that's pretty much it. Nothing crazy there. So let's get started. Okay. So let's start by struct vector. And well, by the way, I'm actually streaming on my laptop because my desktop is still under repair shop currently, so it's gonna be a little bit slow. Hopefully not too much, but let's see. Okay, so cargo check turned on, great. Well, actually, first of all, I like to always, whenever I start a new project, I like to always allow in used and allow dead code. Of course, you want to remove this after you're done with the code, but whenever I'm just starting to implement something, I do this. And I also make sure to forbid or warn in used must use, because in used also includes this subset, in used must use, but this is pretty important to have even when you're implementing stuff. But basically, in used and dead code is very, very annoying and intrusive when you're just starting to implement something. So this is a little tip from me that you could use. All right, so that's great. So that's all we need for that. Now let's actually create our vector struct. Of course, this is going to be a mathematical vector. So let's see. So we have struct vector, and it's going to be an array because, well, we cannot really do something like x, i32 and y because, well, we want our vector to be generic over, you know, any dimension, like 2 dimensions, 3 dimensions, 4 dimensions, whatever. We cannot do this, right? So the better way of doing this right now, I'm just going to wrap a array. I'm going to wrap an array, and let's just say it's going to be i32 with, let's say, 3 dimensions. Okay. Let's see. All right, good. So now we have a vector struct. Let's try to create a vector. Okay, vector. And let's say 1, 2, 3. Would this work? Let's see. Expected i32. All right, there you go. So as you can see right now, we have created a vector. Now the problem is, if you add another element, we're gonna have a problem. Type mismatch, expected i32 3 but found i32 4. And in fact, before that, honestly, let's start with the other problem, which is the fact that if I change the type of these numbers to float instead, we're gonna have a problem, which is the fact that, well, it's expecting i32, but it found f64. So this only works for i32, right? So how we can make it generic over any kind of type, over any scalar type? And by the way, scalar basically means in mathematics these, you know, the components of the vector are called scalars, you know, or like just one single number is called a scalar basically, while a collection of numbers kind of roughly means a vector, but you got the point. Anyways, so how we could do this? Well, we could make some generic type t. We're declaring a generic type of name t. You can call it whatever you want. You could do whatever for that. But anyways, so here let's say t. And right now we could actually use our floats just fine. And as you can notice, Rust compiler is pretty smart enough than other compilers, no pun intended, to actually infer the type of your vector automatically. So here it's inferring that it's a f64. If we made them integers instead, it's going to infer that they're integers, i32 as you can see. If I made them i64, it's also going to infer that. There you go. But now the other problem would be is in the length of the vector. If we add another element to the vector, it's not going to work. So how we can fix that? Well, we need this to be generic, not just specific to 3 elements or 3 dimensions. So how we could do that? Well, we could again declare another generic type. Right. And let's say call it n, for example. Now here we're gonna have a little error, which is, let's see the actual big error. And by the way, Rust compiler is your best buddy when it comes to programming. So errors are pretty good. In fact, the worst is when you get no error but nothing is working. All right, so anyways, expected value found type parameter n. So it's saying that this is not a value. Okay, so here basically an array is expects a like a compile type constant, not a generic type t. So how we can make this, instead of a type parameter, we can make it a value? Well, could say const n, and then we gotta give it some type. In this case, let's say usize. Okay, and now actually our vector is generic over the scalar type and over the dimension too. So we could go wild right now, do whatever, and as you can see, even infers the length right now. Pretty cool stuff. There you go. You could go wild with this. It's fine, right? So that's pretty good. And I like to call my types with proper names. So let's call this scalar. This is the mathematical term. And here let's call it dimension. Okay, constants by convention are like this, are, you know, in this, like, essentially constant naming convention essentially. So anyways, all right, so we got right now our struct vector. Great. So now what? Well, let's try to implement some constructor, for example. Although in this case we don't really need it, but it's a good start. So let's implement vector. Now this is what you would usually do when you don't have generics, but you got a problem. Wrong number of generic arguments, expected 2, found 0. Well, it's saying that this vector right here is expecting 2 generic arguments, but you're giving it 0 arguments. So let's give it some. Let's give it i32 and 7, for example. And now we could actually go ahead and do that. So let's say fnu, this is our constructor, and this is what it returns this, and now we could do this. All right, great. Now we're gonna get some components, and these components would be an array of i32 with length of 7 in this case, and let's say it's gonna return vector of components, and just gonna initialize it with the components, just like what we have done here, pretty much. So let's see if this works. Oh well, my bad. This is a static function, so we gotta do it like this. And there you go, vector new, it actually works. Great, but now if we change the type or the dimension, we got a problem. It doesn't work. Why? Well, because we implemented this impl block. Whatever functions, methods, constants you put in this impl block only applies to this specific specialization or instantiation of the generic template basically. So how we can make it generic on any type and on any dimension for this implementation? Well, we could basically say again scalar dimension, but the problem we need somewhere to get these generics from, so we gotta declare them here too. So let's declare them, and I'm just gonna copy this, put it here after the impl block, and this is how you declare generics, just like here, basically no real difference there. And then you pass it directly to the vector struct generic stuff here, and there you go. So right now we still have a problem because, well, these components are hard-coded. So we gotta make sure to change that to scalar, scalar, dimension, dimension. And now this should be working. There you go. It seems to be compiling just fine. Great, but you can notice that this is pretty annoying to be doing, like to be repeating the type every time. And if you change this, you gotta change that and stuff like that. It becomes crazy, right? So instead of this, you could do self instead. This is like an alias that you could use to refer to this essentially. So this is basically the same thing. The same thing goes to here. Instead of vector, you could just say self instead, which is nice. All right, so right now our vector actually is good. The constructor is pretty good. So next step is, well, let's say we want to iterate over this vector, for example, or let's say we want, yeah, let's go with a simpler example. Let's say we want to get the third element of the vector. Let's say how we could do that. Well, let's try to print that. Let's try to print the first element, for example. Would this work? Of course not, because cannot index into a value of type vector integer 8. Now, as I said, the compiler is your friend here, so run, and let's see what it says. All right, so cannot index into a value of type, pretty much the same error. All right, fine. Okay, and you could even, click on this and it would take you to the error code exactly. So what is going on? As you can see, to be able to index into a type, it needs to implement stdop's index trait. So it seems like to be able to index into some sort of custom type, we need to implement this trait on our type called index. Well, we could try to go ahead and do that. Okay, fine. Let's see how we can do it. So use stdop's index, just like that. Okay, so let's try to implement this index trait. So let's impl index for our vector scalar dimension. Again, we're gonna need this again, right? So impl, unless of course if we want to only implement this for a specific type or something like that. Now so we're gonna implement the index trait for this type essentially. Now here, not all trait items implemented. If you actually run this right now, as you can see, it's giving you some clues on how to fix this. So missing generics for trait index. So it's missing idx, which is basically the index, and it needs to be I guess, I'm not sure, anyways, add missing generic argument scalar index idx. Okay, so it's telling us, let's say we don't know this, let's say it's just telling us to add this there, so let's add it. So how we could do that? Well, let's say this, but well, this is gonna be a type, so let's say we want to index, I think, use new size. And if we actually go to this trait, we could see more about it. It have an idx, which is what we use to index into it, and we have an output associated type. Okay, cool. So now let's see what the compiler would suggest again, because it's pretty important to understand what the compiler is talking about. Not all trait items implemented, missing output and index. So as you can see, we're missing those members. Now in my case, since I have an IDE, I could just say Alt Enter and then implement members, and it would do the job for me. There you go. But if you don't, well, you could just go ahead, look for the index thing, you know, and just copy these, you know, copy this type and index stuff and just implement them basically. But anyways, so here the output. Now the output is basically what you get back after indexing into this type, because it could be anything like, so for example, if you, let's say, maybe index into a matrix, you may get, for example, I don't know, a vector or something, but you got the point essentially. Here the type output in our case would be, when we index into the vector, we're gonna get back a scalar, all right, the scalar type. So we're gonna go ahead and say scalar here, and if an index here, let's see what we gotta do. Well, we're just gonna return self.0 dot let's see, yeah, we're gonna index into this just like that, and of course we're just gonna give back a reference. Now this self output is pretty much the exact same thing as doing this in this case, you know, it's pretty much the same, but again, I recommend to do it like this instead. All right, so that's how you do it. Right now, if we actually play this or run this. All right, my coffee is done. All right, so the first element is 1, which is correct. Great. So now we have indexing on our type. Now let's say we want to get how much, or like how much dimensions in there. So we could say, for example, a.len. But of course we cannot do that because we have to implement this. Now again, let's say we want an iterator, then we have to implement that. Let's say we want this, then we have to implement it. That, we want to implement it. So as you can see, this is very tedious when you're wrapping some type. So luckily there is actually a better way of doing this in Rust. So instead of this craziness, you know, we're gonna go ahead and impl deref instead. So let's impl deref for vector. If anyone have any question, please let me know. Right, scalar dimension. And there you go. We're, oh, oops, what I'm doing. My bad. Right, let's see. Let's put that the declaration there. And now trait takes, not all traits implemented. As you can see, not all traits implemented. Let's implement them all. There you go. So the target would be, in our case, basically what we're gonna deref into. So in our case, it's gonna be this array. We're gonna deref into that array. So let's say scalar dimension. You may not understand what I'm doing right now, but just hang on a second. So if we say self.0 here basically, and well, cool. Now let's try to index, for example, and let's see. Let's run this out. And notice we could actually run this just fine without actually implementing the index type. Let's say we want to get the dimensions of this. Well, we could say .length. Notice that here there's 8 dimensions. So if we say length, now it actually works. There you go. Let's say we want to iterate through this and basically sum this up together. Now remember, we haven't implemented the iter method, but we could actually say this iter and then sum. Seems like magic. All right, and here we gotta tell it what it's gonna sum to. What is the sum type? And let's see this. And there you go. We got our sum of all of our components, just like that. And we haven't implemented the iter method. We haven't implemented the index trait, none of that. The only thing we have done here is we have implemented deref, and whenever it gets dereferenced, basically we dereference into the array, to the internal array, right? And basically with that, it's kind of like inheritance. We're kind of like inheriting the stuff of the array, right? So what's going on here now? Implicitly, what's going on here is that the compiler, if it doesn't find some member item, like in this case it doesn't find iter, what it's gonna do, it's gonna try to deref into the next item, right? So in this case it will deref into the target, which is in our case an array. And it will actually right now find the iter method in that dereferenced in the array after the deref operation, right? So there you go, done. If it doesn't find, even after dereferencing once, it doesn't find the member, then it's gonna dereference again. It's gonna keep on dereferencing until it finds some member that have, like some item that have that, essentially. So just like inheritance, essentially, all right? So now let's say we want to actually mutate this vector. How we can do that? Well, let's just print a, and to be able to print that vector, well, for now let's just print debug it, and let's derive debug in our struct. And there you go. Great. So now let's try to actually say a, let's say the element, I don't know, 5, let's equal to 10 or whatever. Okay, of course we gotta make this, well, first of all, cannot assign to data in dereference of vector i32a. Let's see what the compiler actually says. And there you go, cannot assign to data in dereference of vector i32a. Cannot assign. Trait, here we go, help. So the Rust compiler actually helps you and suggests you what you need to do. It's pretty amazing. Like I mean, I learned 8 languages, I think, or how much programming languages, and I've never seen such a better compiler than this. But anyways, trait, DerefMut is required to modify through a dereference, but it's not implemented for vector i32.8. So what it's saying is that you cannot do this operation because we haven't implemented this trait, DerefMut. So let's actually implement that. So basically just gonna copy that again. Now DerefMut. Of course, make sure to import that stuff. And let's say for vector scalar dimension. Great. Now, not all traits item implemented missing DerefMut. It's missing this member that we need to implement for that specific trait, because each trait has some required, associate constants or associate types actually, and some members, etc., etc. Now let's implement the member here and DerefMut. Now notice this deref takes a reference self and gives back a reference self target, but here in DerefMut you actually get a mutable reference to self. Then you give back a mutable reference to self target. Now notice that DerefMut actually, kind of inherits that target member from the deref. So let's see. If you go to DerefMut here, you can notice that it's actually inherits deref. So it gets those that associated item with it, basically. So that's very nice. Which means that you cannot, of course, DerefMut into a, some different target than what you have derefed into, basically. So it's gonna make sure to lock you up, so you can only use that same thing, basically. Anyways, so here we got DerefMut. What we need, well, basically the exact same thing, but just a mutable reference here. There you go. Great. So now can we do this? Well, cannot borrow a as mutable, and it is not declared as mutable. So let's make this mutable first. And now we could actually do that. Let's run this out and let's see. Okay. And there you go. So right now we have changed 6, we have changed it to 10. And it works pretty much. So right now we have implemented deref and DerefMut. So we're basically essentially inheriting all the items, all the methods of the array essentially. So it's kind of like we're just wrapping the array at this point. Pretty cool, pretty cool. Great. So now what's next? Now let's say we want to create a second vector, you know, some second vector b. So let's remove mutable, we don't need it anymore. Let's say let b is equal to a. So basically we just want it to be the exact same thing as a. And let's say let's print a, okay? So we're gonna have a little problem here. Borrow of moved value a. What does that even mean? Let's see if the compiler could actually help us with that. And let's see. Borrow of moved value a, move occurs because a has type vector i32.8, which does not implement the copy trait. Look at that. There is your hint. Value moved here. So we have moved the value here. And value borrowed here after move. There you go. This error originates in the macro, blah, blah, blah. So it's basically telling it originates in the macro print line, you know. Anyways, so as you can notice, the compiler actually hinted into the copy trait. Basically, it's saying that since we haven't implemented the copy trait into our struct vector, then that means when we use a right here, what happens is that instead of copying the vector, we're actually moving it, you know, we're moving the whole thing into our new variable. So kind of like we're binding this variable, this vector from a, and we're binding it to b. So we cannot use a anymore because we have already moved it to b, right? So now primitive types like this, like vector, you would usually want them to be copied. Like you could say, now let's say copy, okay? Let's derive copy. And copy is basically a trait that anything that is trivially copyable implements. So essentially when something, or when some struct or whatever, when some type implements the trait copy, what that means is that you could easily copy around. It's not very costly to copy. Like for example, vector, like vec, you know, the Rust vec, like, you know, the list thing, or that actually does an allocation whenever you create it or whenever you clone it, right? So it's not copy. It doesn't implement the copy trait because it's not very, like, it's not free to copy around. It's very costly, you know. So because you're going to be making a new allocation, then you're going to copy the data around and stuff like that. So usually such types, you actually move them or explicitly clone them. So here you can notice that the trait bound clone is not satisfied, because if you have copy, first of all, you need clone, because if you don't have clone, you cannot copy in the first place. So you could either have clone by itself or copy and clone. Basically, essentially, copy implies clone. Basically. But anyways. In fact, by the way, we can actually implement debug trait, copy trait, and clone trait ourselves. Derive just makes it easier, essentially. So, but anyways, it basically generates for us that boilerplate code. Sometimes you do want to manually implement them, you know, but for now, let's just keep it simple, okay? So right now, since I have implemented copy on my type, now I actually can use it just like a primitive type, like i32, f64, whatever, you name it. These are trivially copyable by implementing copy or declaring to people who are using our type that this vector, you could copy it around pretty quick. It's not a costly operation to do. So. All right, now let's try to print A, and of course it would work out just fine. There you go. Nice. So it works just fine. Now. So what I want to do next? Yeah, let's say we want to add A with itself, or A plus B. Let's say A plus B. And again, we're gonna get help from the compiler again. So let's see the error, because you gotta get used to, you know, communicating with the compiler. And there you go. It's telling you that cannot add this vector to this vector of the specific types and stuff. So as you can see, it's hinting to this. And note, an implementation of add might be missing for our vector integer 8. So as you can notice, it's basically, it must implement add. The trait add must be implemented. There you go. So what we need to do is actually implement add on this guy. So let's see. Well, basically we're gonna do the exact same thing here. Implement add for vector, you know, vector scalar, blah blah, dimension. Okay, cool. Not all trait items implemented, missing output add. Let's implement these members from the add trait. And now we got type output. So output, well, so output, what it would be like when you add two vectors together, what you get back? Well, the exact same type. If you add a vector 4 with a vector 4, you get a vector 4. So that's basically it. So we're gonna say type output equals self. Pretty simple. Now add self, RHS self. Okay, so here this stands for right hand side. So self is the left hand side of the operation. Now in this case, A is left hand side and B is right hand side, right? Great. So how we could add these together? Well. Now this is gonna be a little bit tricky at first, so bear with me here. So let's say we got some result, array. So we're gonna need to, you know, sum these up together. So what we need is the first value, what it would be. Like if we have just, let's start simple actually. Let's start simple. Let's say, just so I don't overload your brain, instead of overloading the add operator, I'm gonna simplify this by starting with the simple stuff, you know, by just starting with, let's say, f32, 3 elements, for example. Okay, so if you feel overwhelmed, you could just start simple with just implementing it for one single type, then go ahead and generalize, just like in mathematics. Essentially, you may start with a simple thing, then you generalize, you keep on generalizing. Anyways, so how we could do this for just f32 3 dimensions? Well, we got to create a 0. So here it's going to be 0 of, and basically 3 elements, and it's going to start as 0 essentially. Great. So right now we have an array of 3 elements of i32. Well, in this case, actually we want it to be f32. Let's just say this. Okay, cool. So right now we got our array. So let's add these together. So let's say for I in 0 up to let's say self, or honestly we actually already know at this point what is the dimension, so let's say 3. Okay, now let's say result I is equal to self I. Notice here that instead of saying .0 I I just say I directly. I don't need that because I already implemented the deref, which should do the job for me. So it even makes my job even easier, not just the user's job. So let's say self I plus RHS I. Now, of course, this should be mutable. And then what we gotta return is, well, we're just gonna wrap that array in a new vector. And we're gonna return that. And there you go. That's pretty much it. So that's how you do it. We created an array of zeros, 3 zeros, since we have 3 dimensions. Okay, and we have just gone through from 0 to 3 index, essentially. Result I equal to self I plus RHS I. As simple as that. Okay, cool. By the way, just to make sure you're consistent, because you don't know the type, it's not like, it's not necessarily, is it commutative, I think? I don't remember. I think it's commutative. Let me make sure, because I always jumble these terms up. Yeah, exactly, commutative. So you cannot really, like, since it's a generic, you cannot assume anything about its algebraic properties or what methods you have, or that, or like, is it copy, is it clone, blah blah. Like in Rust, in like, let's say C++, in templates, where you basically just, the templates are just, you know, evaluated. If it compiles, there you go, done. If it doesn't compile, it goes to the next template specialization. If that doesn't compile, then it goes again to the next. If any of them doesn't compile, then it just gives you a big giant error wall that you cannot understand anything from it. But in Rust, everything is explicit. You cannot, it's like group theory and like higher algebra, where like you cannot really assume anything about the properties of the algebraic you cannot assume algebraic properties on the stuff that you're you know, handling, essentially. So it's not like in high school where you're just like, yeah, let's just go crazy with them, let's just assume they're real numbers or whatever. So you don't get to do that here in Rust. Wa alaikum assalam, wo G Gearing, welcome to the live stream. So that's hopefully makes sense. So always make sure to like here you can maybe, like, what you could do wrong is that you could assume that this is fine, but here you're assuming that the elements are commutative, which is not entirely true. And in fact, this is not true for F32. You know, for floats, it's not like mathematical real numbers. Floats aren't really commutative, and I think they're not even associative. If I'm not sure, I always forget about these properties. Yeah, exactly. So they're not associative, they're not commutative. Like if you add, let's say, basically if you add A, like if you add B plus C, then add A, it's not the same thing as adding A plus B plus C. I mean, it's gonna be the very, you know, like you're not gonna get like different results, very widely different results, but it's gonna, the precision will be a little bit off, you know. So because this is how floats work, you're not working with the real numbers where like you have infinite precision, right? No, floats have have finite precision of just 32 bits. You know, you're storing these in discrete memory, you know. So you gotta take that in mind. So really make sure to always not assume stuff about your types, because you never know what it could be used for. Okay, great. Nice. Hopefully that made sense. Now let's try to actually generalize this. Well, let's start simple with generalizing the dimension, I guess. I think that's pretty simple. So let's start with that. So let's generalize the dimension here. Oopsies, const dimension. All right, this is gonna be dimension, not in. And oh yeah, I always forget. This gotta go to the impl and not the add trait. The add traits have its own generics, as we're gonna see later. It's called RHS, equal to self by default, but we're gonna see that in a second. Just ignore it for now. But there you go. Right now we could, instead of 3, we can use the dimension here, the dimension here, and there you go. We're done. That's basically how you generalize a dimension in add operator. I wish it was that simple in the other stuff, the other operations like dot product and cross products and whatever. Anyways, for add operator, it's pretty simple to generalize a dimension. Now, what about the type? Now, the type is quite interesting. So let's start in doing that. Okay, so let's say scalar, because we're assuming a lot of things here. We're assuming a lot of things about the properties of the generic, okay? But we're gonna fix one by one. All right, let's see what we're missing. Let's try to see maybe the errors. Let's see if they're helpful there. Okay, cool. Cannot add scalar to scalar. So it's telling me that you cannot add scalar to scalar. Consider restricting the type parameter scalar. As you can see, the compiler exactly tells me what I need to do. It tells me to actually restrict the type to the types that are able to be added together, you know, because I cannot assume that the types, the scalars, actually add up together, because that's not necessarily the case. So if I want that to be the case, then I gotta make sure to restrict it to that case. Okay, so now let's just add this that the compiler told us, and I already implemented the add, so I don't need that. And there you go. Let's just try to run this again. Let's see what we got. Expected, hold on, let's see. Expected type parameter, expected scalar, expected scalar dimension found F32 dimensions. So first of all, it's telling me that instead of F32, we actually need the scalar here. But hold on a minute, wait a second. How we could do a 0 of some scalar? How we could do that? Like, how do you get the 0 of some type t that you don't know? And that's the thing. But let's start simple. Instead of 0, let's just say F32 default. Okay, the default trait basically gives you back the default element of that type. And in the case of F32s and stuff, as you can see, it's just 0. So let's start that simple, okay? And there you go. So this is basically the same thing as we have earlier. But right now, instead of F32, let's say scalar instead. All right, let's see the next error. Okay. No function or associated item name default found for type parameter scalar in the current scope. Function or associated item not found in scalar. So again, the compiler struck again, and it tells me exactly what I need to do. I gotta restrict that type scalar, not just to be addable. And addable to what? Addable, and it needs to give me back an F32, but it also should be default. Like after restricting it to default, I could actually assume that it have a default and just use that. So let's do this. And there you go. Great. Now we have another error again. All right. So what's next? The trait bound scalar copy is not satisfied. The copy trait, so here the trait copy is not implemented for scalar here when we actually create the array. And it's saying that the copy trait is required because this value will be copied for each element of the array. So there you go. It actually tells you exactly why and what you need to do. It's like Can you get a better compiler than this? So the copy trait is required because this value, the value of what? Of scalar, will be copied for each. So it will be copied for each element of the array. So for each and every entry in the array, we're going to copy that element that we got out of default. Okay. And just to make this more understandable, I'm just going to make this into a you know, a variable, just so you understand one thing. Notice that actually we're getting the default value once. We're not getting it like every time in the array entry. We're getting it once, then we're basically passing it here so it can be copied for every single entry. So as you can see here, Rust already told me that I need to implement or constrain my scalar type to copy. So let's actually do that. Okay. Cool. So now what? Now I did that. Let's see what's next. Okay. So what did I assume again? Mismatch types, expected this type parameter. Expected type parameter scalar. Why I'm going through this? Now I could have just implemented this from the start perfectly and yeah, that's it, done. Here's how you do it. But it is very important for you to understand why we're doing things and to understand how to read compiler errors, like errors, and how to deal with the compiler, how to communicate with the compiler is your best guide. So that's it, especially the Rust compiler. So that's why I love Rust. So, well, one of the reasons why I love Rust. But anyways, expected due to the type of this binding. Expected type parameter scalar found F32. So what it's saying here, it expected a scalar, right? Because the result is an array of scalar. But here we have given F32 somehow. But hold on a minute, why? Well, we have added these scalars together, and what we have declared add trait here, we have said that the output would be F32. So we're saying that if you add the scalars together, you get back an F32. So that's why we have a problem there. Because, well, when you add two scalars together, well, you get back the same scalar. There you go. All of this was intentional, just to show you exactly why we're doing things. There you go. So that's pretty cool. Great. Now let's try again. Let's see if this works. Okay, cool. So now we're actually, you know, taking A and B and adding them together, and we're getting back the result. Amazing, right? If we say we could change this to whatever we want, we could make it F32, whatever, you name it. Go wild, you know. Let's make these floats, for example, and there you go. There you go. So it also works with these, it also works with a different dimension, whatever, you name it. Now this is good and all, right? Now just ship your vector library and that's it. Good, great. But then you came, like someone else came ahead and wanted to use your vector with something interesting, and you're gonna have a problem. Now let's say we're working with some scientific computation, or like some scientific application essentially. And the problem with these kind of primitive numbers is that they're limited in size. So like they're actually not like the real numbers, which are infinite from both sides, like the line, the real numbers line, you know, they're not infinite. Once you reach a certain point, you don't have enough memory, so you're gonna go back and like wrap around and just go back again from the other side and go again, and it keeps on going like that. These numbers are, I forgot the term, the mathematical term, but like all right. field that deals with numbers that wrap around. I forgot the name. Modular arithmetic, exactly. So this is like modular arithmetic. In fact, as programmers, we always do modular arithmetic. So it's like in a clock. Oh, I gotta do the charge. I'm now on my desktop, so. All right, hold on a second. Okay, great. So, as I said, like in a... Okay, come on, Windows. What the... Anyways, modular arithmetic. So, what I was saying. Okay, so as I said, the clock here, right? So, once you reach the limit of, 12 hours, you just go back again and start from 0 again, and it keeps on going. This is like the numbers like F32 and stuff. Once you reach the maximum number of that specific precision, you just wrap around, just like a clock essentially. And these are called like the act of actually doing arithmetic, like plus operation times blah blah blah. On these types, this field is called the modular arithmetic. Okay, so modular arithmetic is a system of arithmetic for integers where numbers wrap around when reaching a certain value, called the modulus. The modern approach to modular arithmetic was developed by Carl Friedrich Gauss. Hopefully I didn't butcher his name. In his book, this Quotients Arithmetic, published in 1801. Okay, the familiar use of modular arithmetic is in the 12-hour clock, in which the day is divided into two 12-hour periods. So the time is 7 o'clock now, then 8 hours later it will be 3 o'clock. So simple addition results in 7 plus 8 equals 15, but 15 o'clock reads as 3 o'clock on the clock face, because clocks wrap around every 12 hours. So yeah, like the primitive types, the primitive numbers, once they reach a certain limit, which is, you could actually get that limit by saying, like for example, let's say U32, or yeah, let's say U32 for example. Once you reach the limit maximum, you wrap around. So let's see here. And as you can see, this is the limit of U32. We have 32 bits of precision, like 32 ones and zeros to represent the number. Let's say U64, and let's see the maximum of that. And notice this is the maximum. Now let's say we said +1. What we get in our case? Oh well, in Rust we actually have safety, something called safety in like C++ and C. So the compiler would actually warn you. This arithmetic, or actually not warn you, it would throw an error. This arithmetic operation will overflow. So it's telling you exactly what's going to happen. Attempt to compute U64 max +1, which would overflow. Overflow meaning that it's going to, like, you just reach the limit of that number type, which is U64 in this case. Now, as you can see here, deny arithmetic overflow on by default. Now you could actually disable this. You could say allow. Allow arithmetic overflow. And then what? Oh yeah, I forgot. This is an error that I do a lot, which is I forget this guy right here, which makes sure instead of like, applying it just for the next line, it applies it for the whole project or the whole file. I'm not sure. Anyways, okay, so what's going on here? Attempt to add with overflow. And right now, instead of getting a compile time error, I'm actually getting a runtime error with Rust. So as you can see, this is how safe is Rust, because every single little detail, like, it's making it very hard for me to even do that. But actually, this is how the way to do it specifically, because a lot of times when you're adding up together numbers, you're not thinking about overflow situation. What's going to happen if that number is too big to fit in U64? You're not thinking about that. So it's pretty easy to make horrible mistakes, like blowing a rocket just because of these stupid errors, you know. And I'm not even kidding, like actual rockets got blown away just because of this overflows and this little tiny details. We're humans, so we need compilers to actually guide us in this path. Right? So this is one of the little things that Rust do to make sure you're not shooting yourself in the foot. So how we could actually make this work? Well, in Rust you have to be explicit. If you want this to overflow, this operation to overflow, then you gotta actually make it explicit, make it very obvious, very clear to anyone reading your code or and to the compiler that you want the overflow to happen. So let's say add, actually it's called wrapping, or yeah, a wrapping add. This basically wraps around. Wrapping modular, as you can see, addition. Let's say wrapping add plus. Let's run this out. And we got 0. Why that's the case? Well, because, well, after maximum value, you just wrap around to the first value, which is, in the case of U64, is 0. So this is what happens. It's modular arithmetic. But, well, as I said, I have a scientific application, so I need huge numbers, let's say. So how we can do that? Well, we need something called big integers. And let's look for some library for that. Rust. Now, fortunately, adding libraries in Rust is very simple. No pun intended. Okay, so let's actually copy this. All right. Cargo add num big int. Bam, that's it. You have added a library. Let's go. All right. So now what's next? Okay. So what I want is to use that big num. Now the documentation of every library in Rust is uniform. So like all the documentation is pretty much in the same style, even down to the, you know, conventions of everything. That's one of other reasons I love Rust. Anyways, so let's see. Now we got big U int. As you can see, this is how you do the 0, and this is how you make a 1 in big U int. So okay, and yeah, that's how you do it. So you could say some number to big int in wrap. All right, cool. So let's try to do that. But of course, to be able to do that, I need to import this straight to big int, which actually goes ahead and extend my primitive types so I could actually convert them like this. Okay, so let's go ahead and say use num big int to big int. Great. Now let's see. Now let's go back to our integer type and let's just say to big int, okay? So let's turn these into big ints. There you go. Same thing this for this and same thing for this. But these are an option actually. So basically it could fail to do the conversion, I think, for some reason. Maybe, I'm not sure why that's the case actually. It's weird. Let's see. To big int. Doesn't really say so, but we could look into the source code possibly, maybe. Alright, too big. Yeah, I'm not sure why it's an option. But anyway, let's not waste time right now. Let's just say in wrap. So if it's nil, it's just gonna crash. or if it's none essentially, if it failed to do so. All right, so great. Oh yeah, my bad. Let's actually add these together. Say a plus b. Let's try this out. Okay, we have a little error here. Cannot add vector big int 3 to vector big int 3. Now I'm going to show you why I'm doing all of this, so I can show you why we need something instead of just me rambling around it, right? So this is an application of it, but notice here we got some error that we had earlier back. Cannot add vector big int 3 to vector big int 3. Well, why that is the case? Well, we have implemented add for all elements, like for all generic types, all right? Well, kind of, but well, we have restricted the type to some types, right? So if we notice here in the add block, impl block, where is it? There you go, okay. Here, scalar, we're not really implementing it for all types. We're implementing it for all types that implements add, and that adds up together to scalar, and then that implements default, and that implements copy. Well, let's see which one is missing here. If you go to big int, right? Where is big int? There you go. Let's see which trait is missing here. Alright, so add is there, add assign, bit or div, all of these are implemented for this type. Now one thing that you're not going to notice that this type implements is, let's see, copy. Why? Because big int is not really trivially copyable. Let me see why. Big int sign, it's actually just big uint. Right, let's go to big uint. Let's go to source code. What is the data here? Notice data vector, vec of big digit. And what vec is, it actually allocates memory. So we can grow, so you could basically store any number as long as your RAM is enough. Your computer memory is enough, right? So because vector can shrink, can shrink and can extend, right? So it can extend as much as you need for that big number to store it, right? So, well, so what's next? What's the point? Well, vec is not copy because it's not trivially copyable. When you want to copy, you have to actually allocate new memory, and you have to copy the old, copy the other data to this new vector, which is a lot of stuff, right? So it doesn't implement copy. So if you want to actually support such types that doesn't implement copy, you have to instead constrain your type to clone instead of copy. Now clone is basically the same as copy, but it is explicit. If you want to copy something, you have to exactly tell it when to do that. You have to tell it clone, explicitly clone it, and which of course most types actually implements that, but not most types implement copy. Okay, great. So now that we have implemented clone instead of copy, and by the way, even though we have implemented derived copy and clone, but these derives would only happen if the underlying data is actually able to be copied and cloned. Now in our case, when the scalar is big uint, this array it also derives this copy, clone, blah blah stuff, right? So what happens is that since the scalar, isn't copied, then the array won't be copy, won't derive copy, and so since this array won't derive copy, then this whole vector won't derive copy. So even though when we say derive, we're only implementing this stuff for things that are able to be implemented too, essentially. Okay, so now what's going on? Let's see. The trait bound scalar copy is not satisfied. Well, we have a little problem here. An interesting problem. Because the compiler is constantly asking us to implement copy. Because here, to be able to use this array initialization thing, you have to copy, not clone. So how are you going to solve this? Well, you cannot really clone it, because if you clone it, well, it's not going to work, because here you're just passing a new copy, and like a new clone or a new copy, right? But then the array is still trying to copy that element up to every single element. Now here you would use actually an initialized array, and then you would initialize it, you know, one by one. But that's unsafe, of course, and unsafe is bad in Rust. All right, so how we could do this with safe Rust? Well, we cannot use this anymore. So, but fortunately, there is something interesting in the standard library, in the array. There is something called from fn, okay, from function. So we can construct an array from a function. So instead of just copying one element up to each and every single entry in the array, we actually, for every element, Rust would go ahead and call our function and construct a new element, you know, for every single entry. And we get the index for which index we're actually constructing this value for. So if you want to use that, in our case, we're not going to use it, so no need for that. And here, in what we're going to do, we're basically just going to construct a new default value. Now notice, we're going to construct a new default value. We're not going to be copying, you know. So there you go. Now I don't need this anymore. That's why I made it explicit, this variable like this, because if you do it like this, I'm basically emphasizing the fact that you're constructing it only once and you're just copying it. And here, notice that you cannot move out of defaults because you're trying to move this here. But no, we want to construct a new default value for every single entry in the array. So you got to do this scalar default, right? Inside the function. Great. So we have fixed one little thing. Correct. Great. So now what's next? Let's see what is the other problem. Cannot move out of type, scalar dimension, a non-copy array. Cannot move out of type, scalar dimension, a non-copy array. So what's telling us here? It's telling us that you cannot move the item scalar from this array because that array elements aren't copyable, you know, non-copy array. Move occurs because value has type scalar, which does not implement the copy trait. So since it doesn't implement the copy trait, you cannot just copy new elements and give it back to you. You have to move it, but it cannot move it from the array because then it would become initialized, which is bad, right? So how we could do this? Well, we could clone the value instead of moving it, you know. Or we may be able, depends, we may be able to even give a reference instead, but I'm not sure if that would work in this case. Okay. Yeah, I don't think it would. Well, depends. You have to go through and implement a reference to scalar for add and stuff like that, which is gonna get super messy with lifetimes and stuff. So for now, just to keep things simple, let's just clone stuff up. Okay. All right, great. So now we're cloning the values. And now here, when we change from copy to clone, right now, it is explicit where we actually do the copy operations. So we're very mindful, we're very aware of where we're actually doing expensive cloning operations, you know, instead of just throwing that value around and copying it crazily. So we know that right now here we're doing an allocation and here we're doing an allocation. You got the point. So that's the difference essentially. Great. Now, would this work? Let's see. Still, we have a little problem. Value use of moved value a, because right now, since scalar doesn't derive copy, so a or the vector cannot derive copy. So right now we actually have to clone this. Okay, so let's clone it. And now, and finally, it works. Let's go. So right now we could go wild with those numbers. We could say something like something like this, blah blah, whatever. Okay, and there you go. Let's go even crazier. Let's go wild, maybe with U1 208. That's 128 precision. And look at that number. So right now, big int, actually, we could do, it doesn't end as long as you have enough memory. So there you go. So now you understood why you shouldn't constrain your type too much. Now there is a delicate trade-off here between usability, or like ease of use essentially, and also on how much types, how much generic you want the thing to be. So in our case, basically we could choose to either go with copy, which gonna make it very easy to just copy stuff around and stuff like that, but then your algorithm doesn't work, or your implementation doesn't work for types that doesn't implement copy. Otherwise, you could go with clone. So now we're gonna support more types, because copy is like a subset. The types that implement copy are the subset of clone, kind of. So you support less values. Like big int, you wouldn't support it if you constrain your type to copy. But hopefully you got this point right now. So right now, our implementation would work for anything that is that could be added together, and it gives us back the same type, and that can be able to give us a default value, and that can be cloned. So that's great. Can we do any better? Let's see. Add output scalar, that's for sure. We need this. There's no way about that. Clone, we do need that too. Default, well, here it depends. There you have some options, right? You could either go with default, or if you want to be explicit about what you're actually talking about here, because you're not really talking about anything that implements really default. But what you really want is 0, something that implements 0, that could be zeroed essentially. And for that, we need something. Okay, let me show you. It's called num traits, I think, Rust. Num traits. So if you go here, this is another library. And it implements, it gives you a lot of cool traits like 1 and 0. These are the identities. This is the multiplicative identity. And this is the additive identity, 1 and 0. Okay. So you could basically constrain your type to be either 0 or 1 or both, or something like that. So you could get 0 and 1 from those types. But honestly, default for now, at least, I think it's fine here, because you wouldn't really see too much value in changing from default to 0 for now, at least. But let me show you another thing right now. Let's say we want to implement multiplication right now, because here where this will shine. Because with 0 you could get away with default, fine. But for multiplication, cannot multiply vector by vector. Why? Because an implementation of mul might be missing. So we gotta implement multiply. So how are we gonna do that? Well, let's just copy this. And instead of add, let's just switch this to multiply. Oopsies. Hold on. Make sure to get it from stdops. I'm not even sure what num that is. But anyways. Okay. Implement mul, not add. Here this becomes multiply, and here this becomes multiply. Let's see now. So we have a little problem here. Actually we don't. No, that's not exactly what I wanted. Yeah, I wanted sum actually. I wanted sum. Yeah, let's actually go with the sum implementation. So let's go back. Let's remove this. Yeah, because multiplication is not really the problem that I was looking for, okay? To demonstrate my point. But yeah, I think sum would be better. Not sum, product actually. Product, yeah. Let's say we want to implement some function called product in our type. And of course, we don't have... let's actually make a new impl block. Because if we make it here, we cannot make new values. Like, honestly, let me just do it here so I could show you exactly why that's the case. So, fn product, let's say. So this is a function in vector that is called a product. And this would give you back a scalar. Is this string fine, by the way? Seems fine to me. Great, looking good. Nice. My laptop is screaming for help. Anyways. Alright, so let's see. fn product. Self. So basically, we're going to take a reference to self, and then we're going to give back a scalar. Right? This is what a product is. So, let's say result is equal to... Yeah, let's start simple, actually. Let's start simple. Let's say... Let's actually implement this, not for generic, but let's just make a new impl block. Let's just start simple, implement this for the vector of type... scalar of type f32, for example, and let's say 3 dimensions or whatever, okay? Just so we can start simple here, and what I'm doing. There you go. So let's implement this product function here, great, and let's start simple. So what you would actually, how you would implement it. Now we could go with the iterator route and stuff, but for now let's keep it very simple. So result. 1 days, welcome to the live stream. Good evening. What's your favorite programming language you used on stream? For sure, Rust. Of course, Rust. Rust is my favorite programming language to date. I have learned 8 programming languages up to this point, and pretty much Rust is like beat them all out of the water. Of course, every language like is not as perfect. Like Rust is not perfect. Any language is not perfect. Every language have its own kind of ups and downs, but in general, I think Rust is the best. Because, well, the thing is, Rust is actually have a very steep, learning curve, by the way, and it also takes quite a lot of effort to implement stuff in. But in return, you get a very great robustness, reliability, safety, memory safety, thread safety, asynchronous safety. You got the point, right? And you get this beautiful, amazing compiler, this beautiful community that is uniform with each other, and one build system, one package manager, one kind of documentation. Like any library you're gonna find for Rust, you're gonna find the same exact style of documentation. Here's enum, here's structs, here's blah blah, here's the source code, you can search things up, here's platform, blah blah. You got the point, right? And even down to the same coding style, like the code style is the exact same thing. Like you're always gonna find the dimension, like the constants being like in this naming convention. You're gonna always find this and that, so like the community is working together, they're on the same page. Like you could rely on libraries to just work TM. You could just say cargo add language and cargo add library, and you got the library. There you go. So yeah, it's very, very good. It's like other languages are just very complex for no single reason, you know. But Rust, for sure, it's very complex, a big learning curve, or like big steep like difficulty to learn it, right? But in return, like every time you learn more about Rust, you come to appreciate why it is that way, why it is that complex. So you see that that complexity have a reason behind it, right? But when it comes to, for example, C++, whenever like I even read the whole book of its creator, like, and whenever I learn more about C++, I just hate it more, you know. So instead of loving it more, I just hate it more because it's just too complex for no reason. Too complex. Well, there is actually quite a little reason, which is backwards compatibility, you know, and tech depth, because, you know, Rust is like 40 years old at this point, I think, or something like that, right? So, and it also have to keep compatibility with C, have to keep compatibility with the older C++ versions. You have to keep compatibility with all the crazy compilers out there, because in like Rust, you don't have one single compiler. You have a lot of crazy compilers out there. Everyone is doing his own thing. Like everyone is using his own compiler, everyone is using his own build system, everyone is using his own. It's just too fragmented and too complex for no reason. Like, and CMake, by the way, a lot of people get this wrong. CMake is not a build system, it's a meta build system. It actually was born to just manage this big giant mess of fragmentation in the libraries, right? Where everyone is using his own build system. So what CMake does, it basically gives you a language which you could use to essentially work with any build. Like you could generate any like build files for any build system, like for your favorite build system. So essentially, CMake was born to just manage that mess, right? So it's a mess of messes of big messes, right? That's why I hate C++, because the community is too fragmented, too fragmented. Everyone is using his own compiler, everyone is using his own build system, everyone is using his own naming conventions, everyone is using his own documentation solution. Someone is and people build stuff from scratch, not because there is nothing better out there, but they just cannot really afford to install a new library, because to install a new library, it comes with its own craft, you gotta understand. And someone is using C++ with like C with classes in C++, and one other one is using C++ 23, the other is using C++ 11. It's a giant mess, right? And I'm actually gonna make a tutorial later on like multi-threading, right? On the safety side of that. So I'm also gonna show you what how Rust actually protects you from some stuff that C++ doesn't. But you got the point, right? So I do know how to program in C++. I won't say I'm an expert at C++, but I'm certainly, I think, an intermediate. But hopefully you got the point right now. Just too much, a big giant mess. And Rust have actually managed to fix all of that. But anyways, hopefully that answers your question. I've failed learning Rust 3 times now. I prefer Zig. I watch your recorded streams and hopefully I learn something. I do recommend to start with the beginner book, like the Rust book, right? If you're still a beginner, if you haven't already gone through this, go through this. And after that, I recommend, hopefully my channel in the future, I'm gonna make more of such tutorials like this one. This is actually the first tutorial that's gonna be helpful for people who are learning Rust. But this is a bit advanced tutorial for this one at least. But later on, hopefully I can make more basic ones. But on the other hand, I recommend, what is he called? John, I don't remember his name honestly. Rust. Bruh, come on. Yeah, exactly, this one. But yeah, this guy right here, he have a channel, John, I don't know how to spell his name, but there you go. He have a channel. He have a lot of good, cool videos about like for intermediate Rust people. So after you go through that guide, you could hopefully find some of the videos of this guy. He have a lot of great videos. I learned a lot from him, so I surely recommend that. And of course, at the end of the day, you're really gonna have to look into the documentation of Rust. That's basically the best thing you could do, right? So just go ahead, make yourself comfortable with the documentation. Where's the documentation? Not this. The standard documentation, I think. Rust std docs. There you go. You know, get familiar with this. Like for every module, you have a top level module documentation, which just gives you an overview of that specific concept. Like for example, let's say you want to go with iterators. You want to learn iterators. Just search for iterators. Now this is basically the top level module documentation. Here it basically tells you why you need iterators, blah blah, like an overview over iterators, etc etc. As you can see, lateness, infinity, blah blah, right? But then once you go through an overview of this iterator stuff, you could go to a specific stuff right here. You could branch out to specific things like the iterator trait. You could check that out and get more information, like a API reference kind of thing, and you have examples and stuff like that. Pretty great. So hopefully that helps for that. And yeah, right. Hey bro, appreciate your Roblox the videos. They're very helpful. Thank you so much. You're welcome anytime. Alright, so hopefully that helps. What else I wanted to say? Yeah, I think right now let's just go back to tutorial if there's no questions. So, okay, so what I was saying, yeah, we were implementing the product thing. Hopefully I didn't forget something I was doing. But yeah, anyways. Yeah, as I said, these num traits essentially gives you a lot of cool traits that you could use, like for example identities right here. But let's first of all see what this actually is useful for. Let's make a product function, and for now we're just implementing it for f32 just to keep things simple, right? So f32, and then we're going to generalize it later. So let result is equal to 1. We're going to start by the identity, the multiplicative identity. So 1 times any number would equal to that number. So x times 1 would always equal to x. That is why x is an identity. And a multiplicative identity, right? For plus though, the identity of a plus operator is 0. So x plus 0 is equal to x, right? So the multiplicative identity is 1 because anything times 1 is x. Like anything times 1 is itself, right? And in terms of addition, anything plus 0 is, well, itself. And that's why this is the 0 is the additive identity and 1 is the multiplicative identity. Anyways, in this case we have the multiplicative identity because we're going to do a product, and a product is basically the multiplication of all the elements in our array, you know, of all the elements we have. So that's nice. So we're going to start with 1 because anything times 1 is itself, right? So let's return result. So if you have any components, we're just going to return back the identity. Great. So return result. We don't need return actually in this case. It's okay, expression. We could just do this. Okay, so now let's go through all the components, I think. Oh yeah, it should be f32. Alright, so now let's go through all the components. For component, in components, in the self though, well, self. I think we could probably just say this, since we have deref of vector is not an iterator. We could implement iterator for vector, but anyways, let's just for now, I think let's deref it. I think, yeah, there you go, and you get that. But yeah, let's keep it simple for now. Let's just say self.0, right? As simple as that, and you get the components back. So now let's say result times equal component, right? And of course it should be mutable. And there you go. That's basically it. Now, if we take the, let's just remove the big int for now, for a second. Let's just say, I don't know, 2, 3, 4 maybe. And let's get the product of that. Iter dot product. Okay. Oh no. Oh, it just should be f32 because we have implemented it for f32 for now at least. Okay, great. So let's say a dot product now. Yeah, this should be f32. Okay, there you go. Now product. Okay. So products, of course, would basically multiply these things together and gives us back the result. So it's going to say 2 times 3, which is, well, 6, and 6 times 4, which is, I think, 24. So this should give us 24, right? And there you go. Okay, great. So what happened here? And we could even like debug here and see exactly what's happening here. If you don't know this thing yet, so you can debug and you can see exactly what is happening if something doesn't work correctly. There you go. Okay, so now this is our properties and this is our stack of calls. So we are in the products function right now. We have came from the 8works function, you know, and then we have came from that, and right here just the Rust stuff. Anyways, so right now let's step in. So we got result equal to 1. Now for every component in the array, let's see what we're gonna do. So result is 1 right now, as you can notice here. Now what we're gonna do, we have component is equal to 2. So because it's the first element in our array, if you notice here, there you go. So now let's multiply the result with the component. So 1 times 2 would be 2 because anything times, that's why we have made this to be 1. So yeah, anyways, let's go forward, and as you can see, results equal 2, and we go again, 6, 24, and now we're done. Let's go return the result to the caller and it gets printed. That's how it goes. All right, so just in case if you don't know debugging like this, that's just a little introduction to that. Anyways, so what's next? So now what we need actually is to generalize this. How we could generalize it? Well, let's start by making it generic over n, because that's, I think, simpler in this case. Yeah. So let's say const dimension usize. So basically, if you find something very challenging, you start by the simplest thing you could do, by just implementing it for one type, for one specific kind of specialization of that generic stuff. Right, then you could keep on generalizing it bit by bit. So yeah, so right now we have made a dimension. Great. So now what? Yeah, we don't have to change anything because we're already iterating through the whole thing. So that's basically it for the dimension. Pretty simple. Now the scalar. This is the boss. Okay, so scalar like this. Now you're gonna find a problem. Cannot multiply a signed float by scalar. Well, here we're assuming that we're multiplying by floats, right? So how we can get one of whatever type that is of scalar, you know? It could be big int, it could be whatever, complex number, who cares? Whatever. So we need the multiplicative identity. Now to do this, we need this library, numtraits. So let's add this library. Cool. So we have added it. That's basically it. So now we get access to a nice trait called 1, identities 1. So if we go here, defines a multiplicative identity element for self. So basically a times 1 is equal to a for every element a, or for every a that is, that is part of self. So yeah, same thing with this, 1 times a. So basically they're commutative. These are the laws. So it defines a multiplicative identity elements for self. So basically the required methods of this trait to implement this trait is that you gotta overload this 1, returns the multiplicative identity elements of self 1. This function should return the same result at all times regardless of external mutable states. For example, values stored in TLS or in static mutes. So basically it's gonna be pure function. It shouldn't, mutate stuff around. Okay, set 1, and these are the provided methods. Now as long as you implement this required method, basically you will get these for free. I think, yeah, it will implicitly implement these. Set 1 sets self to the multiplicative identity elements of self, and is 1 to check if it is 1. Turns true self is equal to the multiplicative identity. Okay, and you can notice that there is some implementations on foreign types. So it's already implemented for F32 by F60 for F64 I8. Basically all of these are implemented by the library, by this library itself. Now another library, like for example big int, if they're creating their own kind of integer or whatever and they want to implement this identity 1, like the multiplicative identity, they're going to import this library, they're going to import this trait, and they're going to implement it, right? So for this all to work, your community got to be uniform. Like they're going to agree that this library is the one to go for these things, which the rest community agrees mostly that this is the library to go for numeric traits, okay? For things like this, like traits 1, multiplicative identity, whatever, you got the point. So that's great. All right, so now let's see. So let's say what is called 1. Okay, so let's say scalar 1. But of course, to get this element right here, we cannot assume that the scalar have that, so we gotta make sure to constrain it. So we gotta constrain it to some to 1, essentially, to have the identity. Is that how it goes? There you go, numtraits 1, I think. Defines a multiplicative identity elements for self. Great. So now, as long as I have that, I could call 1, and now I'm going to get scalar that defines the multiplicative identity. Great. So we have solved that little thing. Now binary assignment operation times equal cannot be applied to type scalar. Yeah, why that is the case? Because we cannot assume that we can, use this operator on it, multiply equal. So what we gotta, let's see what the compiler would say. As always, as I said, always go, the compiler is your friend. Errors are pretty actually good. So plus small assign. So let's also constrain this scalar to have mul assigned, so we could use this operator on it. And of course here we gotta return scalar. And now what? Cannot move out of self, which is behind a shared reference. Cannot move out of self, which is behind. Ah, yes. Oh, yeah. Self.0. Because we're trying to move out of that element, which would make the thing not work out. So here we could do two things. We could either, again, implement it for copy, like constrain the type to be copy, or we could say this, right? And here also we have to, even when we do this, we have two kind of things that we could do. Now here, this becomes a reference of scalar, not a scalar. So you have to change either the RHS to be a reference instead of a scalar, or you could constrain it to clone. Depends on your, you know. So that's basically a choice you do. Depends on your use case. So here you could, for example, say clone. This is basically the easiest way to do it, but of course it's very expensive, because right now for every single element in the component you gotta clone it and then times equal, which is not very great for something like big int, which will allocate memory and stuff. So instead of that, otherwise you could basically do this. Instead of clone, you could say mol assign. Now mol assign have an interesting thing. So you have RHS, right hand side type, because right hand side doesn't necessarily be self, which is the default, but you could change that to be anything you want, which is going to be useful in a second when we're going to do something interesting. Just hold on. But I think, how do you, what? Yeah, it's called RHS like that. And you could say equal to, I think, reference of scalar, right? But I think, hold on. I think I'm missing something here. Let's see the compiler, hold on. Probably doing something stupid here, but let's see. And I don't need clone though, right now. Let's see, times equal component. I'm not sure why I cannot really give it this. Weird. Okay, it works. I'm not sure why the IDE is going crazy for whatever reason. Now here, once you deal with references, you go to the lifetime craziness, which is, well, another level. So explicit lifetime needed here. So notice that the compiler tells you exactly what you need to do. So you could say this. Right. And by the way, I don't need this. Let's just import this. And now I'll just copy this. Okay, let's see. I'm not sure why the IDE is going crazy there. So you see it, type RHS not what? Right, what are you talking about? I'm very confused right now. Either way, references are pretty hard to deal with anyway. So for now, let's just not waste time on this. I'm not sure what I'm missing here. Probably doing something stupid. But anyways, let's just go ahead and import this. And for now, let's just constrain it to clone, because that would work also for, at least it's better than copy. It would also work for big int, for example. So component clone, although it's not as efficient. But anyways, I'm not sure what's happening there. All right, what's next? So now we have that working, great. So now we could use whatever kind of thing we want. Like we could say, I don't know, for any type, for any kind of dimension, doesn't matter, and it's just gonna work pretty much. So right now we have implemented the product, and I think okay, hold on, what's going on right now? Okay, there you go, 120. And now honestly, for you know, binary operations like this, I think it makes more sense for this, instead to be default, it should be the, honestly no, it's fine, it's fine. We just need some default value really to just initialize this. We don't care, we just want to initialize it basically. So yeah, that's fine, no need to change that. But for sum, for example, if we want to implement sum, let's say we're gonna make another impl block, and now you know why there's multiple blocks and you have to constantly, you know, go ahead and declare your stuff. But anyways, so right now instead of 1, we're gonna need 0 for the, because we're gonna have a sum right now, and a result, instead of scalar 1, we're gonna have 0 instead, right? Instead of here we're gonna have plus equal, instead of mul assign we're gonna have, you know, add assign, I think. Okay, let's import that, and this would work just fine. So if we sum this up, we're gonna get our sum, and for any generic type, whatever that is, as long as it, you know, meets those constraints that we have done. Now of course we could indeed drop one constraint there, in fact a lot of constraint, but we'll see. Let's see, where is it? Product sum. Yeah, all right, so great. Now add assign, well, basically when you implement add, you're not implying add assign, because add assign and add could have, you know, different semantics, you know, like for example in big int, add assign could possibly be, for example, more optimized, since instead of creating 2 copies of big int and then adding them together and then setting the result to the variable, you just plus equal, you just, you know, in place, you know, add in place. So that's why even if you implement add, it doesn't implicitly means that you have add assign. So in some sense, add is actually, or add assign is a subset kind of add, well, not necessarily, but you got the point. Basically there's more types that probably implements add, but honestly no, that's not necessarily the case, I guess. Yeah, so it could have some types that only implements add assign, you could have types other than that only implements add, but you got the point. But if that's the case, you could basically say, for example, add instead, and just say equal to result plus. But now yeah, that's fine. Okay, so, and you could do it like this. So and the other thing that we could do is, we don't really need, we could drop the 0 trait too, we could drop that constraint too, and the more constraints you drop, the more elements you could use. So we could say this instead, because not necessarily all the structs you're gonna find in the wild gonna implement, for example, 0 and 1 and stuff like that, although it applies to them. But anyways, so here instead of that we could possibly say self.0, we could go get the first element, right, as the result, and then get the other elements after the 0, so from 1 up to the end, you know. And now the problem with this, no, let's say clone, because references are tricky to deal with, especially for generics, because you got to deal with lifetimes and stuff. But anyways, so external linter, consider further restriction this bound. What I'm missing? Did I miss something here? Ah, yes, my bad. So output scalar. So output should be equal to scalar. And now this would work just fine, but now we could use our implementation, like the stuff that the types that we use it with doesn't have to have that 0 thing. But here we have a little problem though. We have a little solid problem here. We're assuming that there is like, you know, one element at least in the array. What if we have no elements? I mean, you could have a vector of 0 dimensions. I don't know if that would be any useful, but you could. And of course, since you don't have any elements, like Rust cannot infer the type, so you gotta give it to it explicitly. You gotta tell it what type. Let's say 32, whichever. And here for the dimension, we're just gonna tell Rust to infer it. I think you can infer it from the array, maybe. Let's see, type provider is expected. Well, I see. So it seems like it's still not implemented, but I think it's, yeah. So like it's gonna be in a future version of Rust, I think, for at least for the constants, compile time constant. But anyway, for now, I'll just say 0 explicitly. And there you go. So let's see what's gonna happen here. We're gonna have a runtime error right now. Index out of bounds. The length is 0, but the index is 0. So we're assuming that we have at least one element in this. And like when we use the identity element as the initial value, which would work with this kind of thing, and it would just return 0 or 1 depending on is it the sum or the product. But basically it would return the identity elements when it's empty. Now here, if we want to do it this way, we gotta make sure explicitly that we at least, like, the dimension is not equal to 0, essentially. So the dimension is equal to 0. Well, now you have a problem. Here you could return the identity elements, but if you want to return the identity element, you have to implement the trait again, which it's like you didn't do anything interesting. Kind of maybe shaved off one allocation in case of big ints, possibly. Yeah, kind of. Other than that, not really much. You still have the same constraint essentially. But basically here you could say, other than that, you could make this an option instead. So instead of a scalar, it's going to be an option, you know. And if dimension is equal to 0, then you would just return none. Else, if it's not equal to 0, then you're just gonna do this, right? Mismatch types. Expected option scalar found. Yeah, here we're gonna say some results. So if dimension is equal to 0, then we're gonna say none, otherwise some. So here, as you can see, there's a lot of ways you could go about it depending on your use case, but I'm just showing you the ways you could go about it essentially. But here in this case, none, since there's 0 dimensions in this case. But yeah, depends on you. So pretty cool stuff. So what's next? What's I wanted to cover next? Now you could see why this is. Now we could use, instead of this, we could use the functional way. I honestly prefer the functional way, though it's a little bit trickier when it comes to generic types and crazy stuff like that. But let's see if I can manage to do it. Result, right. Well, not result, self. The iter. Now we could indeed say just sum, right? You could say sum because this is already implemented into the iterator, right, by Rust standard library. And here we could say that the output is scalar. But here it's telling us that it cannot make a scalar by summing up an iterator of elements of type a reference scalar. So we gotta make sure to clone every element in the iterator, or otherwise make it so it works with references, which we're not gonna do for now because that's a little bit more advanced. A value of type scalar cannot be made by some iterator over elements of type scalar. Why? Yeah, because some I think have a special trait thing or whatever. Yeah, so let's just use reduce, okay? So reduce, and reduce is actually very similar to what we had here, option scalar, you know. So reduce actually returns an option self item. And what you do is basically you get, hold on, A and B, I think. Yeah, a closure essentially. A and B, and return a new element. This is exactly the same as we have done, just in a functional way. A plus B, I think. Right? Yeah, exactly. Morning. Hello, hello, OG Gear. And as you can see, that's basically the exact same thing as we had before, but functional programming. And instead of A plus B, we could probably say scalar add instead. Yeah, I think so. There you go. Okay. So instead of that, you could just say this, right? That's basically how you do it functionally. So it's one-liner, pretty cool. And I love this because, like, when it comes to, you know, this way of doing it, you know, like the imperative way of doing it, it's, you have to scan through the whole code to understand what the code is doing, right? But in functional style, you can understand exactly what the code is doing just from looking at it. It's pretty amazing, honestly. The same thing but here notice that, well, of course this is an option because the reduce essentially gives us back a none when there is no element. Now we could use fold instead. Now the other thing that we had before, the other, well, let me actually leave this so we could basically contrast this implementation with that other one. So this option scalar, you could use reduce, but this is a scalar. So instead of this, what we could do, could return instead self.iter dot cloned dot fold instead, fold, and here the initialization value. So we could say the multiplicative identity. So scalar 1 that's the initial value, and then you have a similar thing as this, I think, if I'm not mistaken. So scalar add, no, oh yeah, here we have mul assign. Oh yeah, mul, but here we cannot use mul assign, we have to use mul in this case. So I think this is basically okay. Now you could basically see the difference between fold and reduce. Reduce would basically, you don't need an initialization element, and it would return back an option. It would be none if there is no elements, and it would be some, but you got the point. And fold, you could actually give it an initialization element, and it will always give you an element, right? So that's essentially it for that one, I think. Now the other thing that I'd like to cover is it's saying 1 because there's no elements. Cool. And let's maybe, is there anything else we could do here? Like for example, this one we may be able to make it functionally. Okay. Product sum. What else here? Default clone. Now let's see. Yeah, let's say we could do it like this. There's a lot of ways to go about this, actually. There's really a lot of ways to go about this. Hold on. How this actually stops? What? Oh, it actually infers it, I think. Yeah, it infers it from the output. Yeah, I see. I see. So let's start by a simple translation. 0 dimension dot map and index, and you could basically say this, I guess. Let's just say I there. And then do we want fold or reduce? Well, actually we need to use fold. But you know, I'd actually rather do it like this. So you would just say fold. So how we can do that again? Iter fold, yeah. So iter fold, and the initialization would be this guy, and you would have a closure, A and B, whichever. Now notice that this would give you references, which is not going to work in our case, so we're going to make sure to clone this for like every element would be cloned in the iterator. And so now we have B becomes a scalar, but of course A is actually an array right now, so we gotta actually say yeah, it's actually quite interesting because we have this array which is, yep, because right here we're gonna need the index and stuff. Actually we could essentially go through the result, I guess. I think I don't want to honestly spend time on this, but let's just see real quick if we can do this. Iter_mut essentially. But yeah, it's tricky right here with functional because you have mutability here. It's not pure and stuff, though it's doable, but let's just not waste time for now on this. Okay, so that's basically it for that one. Now, here's another thing. What happens when you multiply a vector, let's say a vector 1, 2, 3, with some scalar value? Or yeah, pretty much what happens? But you cannot do that because you haven't implemented it. So, and in fact you haven't implemented mul. And by the way, I don't really need the sum and product. They're useless in this case. You know why? Because we could easily, since we deref to the array, we could just say iterator sum just using the Rust iterator stuff. So no need for these. They're already implemented by the standard library for the iterators, so no need for those. Just wanted to demonstrate for you some concepts. DerefMut, blah blah. Okay. And honestly, in my case, I don't really need the constructor. It just more stuff for no reason. So you could just say this. I don't need that either. So yeah, this is fine, I think. And now cannot multiply integer by integer. Okay, so how are we gonna do this? Well, can you add a vector like scalar to a vector? I don't think you can, or can you? My brain is foggy right now. Let's ask the AI. Can you add a scalar to a vector? You can multiply a scalar to a vector, but can you add that? I don't think you can. Yes, you can add a scalar to a vector by adding. Seems like you can, but anyway, whichever. Okay, so let's start by a scalar. Anyway, plus whatever. So we're gonna add this scalar plus to every single component in the vector. So how we could do that? Well, let's just
I guess start with this guy, maybe. Now add, as I said before, have another type called RHS. As you can see here, RHS. Now, before we couldn't actually do this for some reason. And now I have to figure it out. I think maybe it was associated type. Is that the case? What? Let me go back to the documentation though. Pretty simple. Rust add trait. And that would help me out there. Where's RHS? Come on. Bro, what? How do you deal with RHS? I'm sure I worked with this before, but it's just weird. What about stdops, the RHS? What? Are you kidding me? Probably missing something very stupid. Why it's like this instead? Very weird. Is this old documentation or something? Okay, there you go. No, no. That's a declaration. Oh, do you just like pass it directly, I think? I guess maybe you just pass it directly. Hold on. Maybe. Let's just remove this for a second. And if I said self here. Ah, yeah, my bad. I think you just pass it directly. Yeah, seems like it. So, scalar, of course. Yeah, pretty much you just add it directly. I told you it was probably some stupid thing that I don't remember. So yeah, you just add it directly like that. Cool. So as you can see, by default, it's just self, which is in this case scalar. So right now, let's actually do this. Add, and I'm quite surprised that the documentation doesn't talk about RHS. Weird. But anyways, output is equal to scalar. I don't even remember where I've learned this stuff. Maybe just by trial and error. Not sure. Anyways, whatever. So let's see. Add output. Okay, so here's scalar. So hold on. What? No. Yeah, no, I don't want it here. I want it here. Okay, here. So in this add trait right here, instead of RHS self, I want the RHS to be scalar instead. So the right hand side would be a scalar. Not here. I don't want to change this for the scalar, you know, but for the actual object, like vector plus some scalar. So here what's going on. Yeah, right now we just have an RHS, pretty simple. No clone. And that's how you do it. There you go. That's as simple as that. Now 1, 2, 3 plus 5. So 6 plus 5, 11. Oh, my bad. It's gonna add them for every component, yeah. So 5 plus 1, 6, 5 plus 2, 7, 5 plus 3, 8. And basically the exact same thing with the multiply operator and stuff. But hopefully right now you got the general point on how you do this stuff. And yeah, I think I've covered most of the fundamentals that I wanted to cover on this topic. Yeah, there is another one, which is to implement traits. Like, yeah. let's just cover one more thing, I believe. I think that's the only thing that I didn't cover just yet, which is implementing traits for your types. Okay, so let's say, yeah, which one actually needs the multiplicative identity and stuff? Yeah, it was that sum and product, but I removed them. Yeah, stupid stuff. But anyways, on the sum and product that we had before that needed the identity element, or the identity, right? So for those, let's say we had vector inside of a vector, you know, vector, 2D vector, right? So vector, you know, something like this. I mean, I guess we could do that. So, yeah, I think so. And you could probably also say this. Power of generics. Cannot vector to vector. Maybe not. I mean, it should be possible, but what? Weird. But anyway, let's not go wild about that for now. So let's say you have this vector of vectors, right? And you want to sum them up together, like just like before. But the problem is that if you remember, our sum method needed these vectors, or like needed these items of the vector to have an identity element. And actually it does make sense for our vector to have an identity. So let's implement, so how we can do that? Well, we're just gonna add the num traits, great. And we're gonna implement that type for that identity thing for our type, right? So let's implement 1. Let's start with 0, fine. For, well, for what? For vector, scalar dimension. Yeah, let's just do it ourselves, fine. Scalar, comma, const dimension size, usize. Okay. All right, let's implement the members of this. Now, basically, I'm showing you how you can implement some trait for your thing. Actually, I already shown you, like for example, add, but I'm showing you, for example, for 1 here in the identity stuff, etc. There you go. For example, here to implement the 0 identity, like the additive identity of my vector, I have to implement this trait from the num traits, and then I have to implement these 2 functions. These are required, I think. So here 0. How we could check, how we could give it 0 element? Well, we're gonna make sure that scalar actually needs to be 0, and then we could basically just say std array, I think. Yeah, essentially just like that. Just say this, copy that, and we're gonna say vector or self this, and instead of default we're gonna say in this case 0. Yeah, so here we're basically constructing a vector of components. Every component is a 0, so that's great. Weird. Anyways, and for is 0, so is your type is 0 or not? How you can check? Well, let's say self.components dot components is basically 0. Well, let's just, since we have the deref, we could say iter dot all and any. So if, yeah, all of the components should equal to 0 for the vector to be equal to 0. So all the, and since scalar implements the 0 trait, we could say is 0, I think. There you go. Scalar is 0. And yeah, that's basically it. We have implemented right now, I think. Did I miss something here? Maybe I did. Let's see. What? Yes. Yeah, I see. So the zero trait actually requires you, I think, to implement some stuff. Hold on, let's see. Trait bound scalar default is not satisfied. The trait default is not implemented for scalar. Required for vector to implement add. I'm not sure why add is needing default though. Required by bound in num traits 0. Required by. But either way, it's what it's telling me for whatever reason is that you want to implement default for the scalar, so you could add, so you can implement the add. Yeah. Weird. But hold on, I'm implementing 0. What? I'm confused right now. Let's see. So what it's talking about right here? It's talking about this line. And it's talking about this line. I'm not sure what's happening here. That's super weird. But yeah, fine. Let's implement default and see what's gonna happen there. I'm not sure why it's needed that. I mean, I'm not implementing add here. Or maybe I'm missing something. What? Trait bound scalar clone is not satisfied. This is super weird. I'm missing something here. Weird. Either way, you could say right now 0, and you're gonna get the 0 vector. And yeah, I cannot infer the dimension from this, nor the type, pretty much. So you gotta make sure to explicitly tell it. Say F32, 4 elements, whatever. And there you go. There you go. And you can check if your A is 0 or not. There you go, true. Now, if this is the library, what I would add as a final touch, I guess, is to add some aliases just for convenience. So like you could say type vector3, because vector, let's start with 2. Vector 2 is very common. So you could say vector, and here you could say t, some scalar value essentially. And you could say vector scalar, type scalar, and then dimension 3, right? Or 2 actually in this case. And vector 3, because these are pretty common. Vector 3, vector 4. And yeah, right now, instead of saying, for example, this, you could say this. And most people even go ahead and say, like most people just use the scalar to be F32, for example. So you could, even if you want to, you could make some other types, or you could just do it here as a default value. You could say F32, for example, as a default value here. And now I don't even need this anymore. And there you go. Now your user of the library could say vector 0, and there you go, that's it. So yeah, same thing with the other traits and stuff. So hopefully this gave you some foundations. I hope that I didn't miss anything. I don't think I missed anything, at least for now. Cannot really think about anything else I'd like to give you from my knowledge that I learned in the hard way, because there isn't a lot of resources about this. So it's been 2 hours and 23 minutes. Hopefully I have done my mission. So yeah, I think that was it for this video. So I'm just gonna give some time for any questions. Is there any questions? Let me know right now before we end the stream. If there's any questions, let me know. All right, so yeah, if there's any questions or things that I didn't cover, let me know. So hopefully this video would be enough for you to get started with generic programming in Rust. Hopefully, try to do my best there. So yeah, if there's no questions, then we can end the stream. Did I miss anything? Right. Let's see. Num traits, identity. Ah, yes. By the way, one other thing. I'm glad I have remembered. But there is actually some other crazy cool stuff here. Like, for example, the inverse trait, which basically is a unit operator for retrieving the multiplicative inverse or reciprocal of a value. So we could implement that too by basically saying 1 divided by all the components of our vector, essentially. So it is going to give the inverse. So 7. Yeah, 7 inverse. So the inverse of a value times itself. Like basically here, some x times x dot inverse is going to give you back 1, the multiplicative identity. Because, well, 1 divided by x times x is x divided by x, and x divided by x is going to give you the multiplicative identity, essentially. All right. And of course, you got to make sure to, if you implement these, you got to uphold these kind of laws. So if you implement, for example, in fact, if you see here this inverse, it's going to need the multiplicative identity, I think, maybe. Doesn't seem like. But you would need it. Like, for example, in group theory, by the way, group theory, you have some axioms, I think, or laws. I don't remember. Yeah, I think axioms, but let's see if I can find it here. That's crazy stuff. Nah. Probably I missed it. It's gonna be first. No. No. Let's see. Accent. There you go. I think. No. Hold on. Yeah, there you go. At least he's using the axioms of those. But basically, for a group, in group theory, in mathematics, higher level mathematics, what you have is that what a group is, just roughly, I'm not going to give you like a university grade rigorous definition, but basically it's like the type, like the set, actually. In our case, it's kind of similar to a type, right? The set, which is in this case scalar, and the operator add. But of course, it needs to be associative, so this is not exactly the case. And since, for example, at least for floats, floats are not associative. So a plus b plus c is not the same thing as a plus c plus b or something like that. But yeah, that's just a little thing to get you curious. Maybe you could try to look into this. But essentially why I've shown you this is because there's another axiom for, I don't remember, but I think the identity. But basically and there's also the inverse axiom. Now, why the identity is there, at least to my knowledge, because it makes things much easier. It makes it much easier to define the inverse, because if you have the identity, the multiplicative identity, for example, you could easily implement the inverse for the multiplication group, right? Or the multiplicative group. But anyways, that's just a little branch that you could check out on your own. um, I'm very interested into this stuff, but I'm still very beginner. I don't know, it's like I'm very interested, but I still couldn't find really some good resources that I could, at least for my own kind of how I understand stuff. So but yeah, that's pretty interesting stuff. It's like abstract algebra, you know. I've got very interested into it just from generic programming with Rust, because in abstract algebra, essentially what you do is that you don't, it's not like, you know, high school arithmetic or like high school algebra, basically, where you just assume that the stuff like the algebraic elements are like commutative and they're associative, and you assume everything about them, right? But that's not necessarily the case in when it comes to higher level mathematics. Like in abstract algebra, you cannot really assume anything. Well, not anything, but like there is some axioms, but you got the point, right? So you assume very little things. If you assume anything, you gotta state it explicitly that you are talking about this kind of things, right? And the more you constrain your proof, the more it becomes harder to prove, right? But the other way around, the more you let it loose, the easier it becomes to prove, but your proof doesn't apply to more, like it applies to less types because you have more constraints, right? It's just like a delicate kind of, I don't know, I just find this stuff fascinating at this point in my life. I've always seen abstract algebra and like theoretical mathematics just as boring and stupid, that they don't have any application. But right now, thanks to Rust generic programming and stuff, I could really see the value in such things, and I finally started to really start to click on me on why you may need such cool stuff, right? But yeah, pretty much that was just a little branch right there of my own experience, right? But yeah, what I wanted other than that, yeah, let's check the other traits, right? Let's check the other traits before we finish up. Let's see. I want to basically not go back to this generics anymore. I want this video to give you enough information to go wild. So yeah, so you can check the documentation here. Just make sure to check these out. They're pretty cool stuff. Is there anything else? Yeah, the other thing is that you may find this very tedious. Like, let's say, for example, you don't want to go through all this crazy stuff. You just want to implement, let's say, some algorithm for all number types. Not for all, like you don't want to specifically say that it should be addable and it should be multiplicable and it should be copy and it should be blah blah. Instead of that, you could just say this. Like you could use this trait instead. If you, well, let's see, where's num? I think it's called. Yeah, I think it's called num, but where is it? There you go. Okay, I think this is the one. The base trait for numeric types, covering 0 and 1 values, comparisons, basic numeric operations, and string conversion. Basically, if you work with this num, like if you constrain your type to this num, then you would have all of these kind of properties, these algebraic properties that you usually assume you have in normal arithmetic, essentially, I think. But yeah, generic trait types implementing basic numeric operations. So yeah, basically num, as you can see, implements all those basic foundational kind of traits you may need, like the identities, the partial, like the equality stuff. Like if some type implements this partial EQ, that means that you could basically compare them for equality. And there's these num OPs, and as you can see, this one already implements for you all of this stuff. It gives you add, it gives you sub, it gives you multiply, division, remainder, which is modulo essentially, And yeah, just check out the documentation. You're gonna learn a lot of stuff from here. The documentation is very interesting. But basically, instead of this, let's say, for example, let's say you just want to make some sort of little, I don't know, maybe lerp function, for example. And you just want this a to be any kind of numeric type, like just primitive. You don't really care, right? You don't want to go crazy with generics and stuff, so you could just go easy and just say num from the num traits. You're gonna import that, and you're gonna say that a is t, b is t. Let's say, I don't even remember the, I think it's alpha. Yeah, anyways, let's say t, and here let's say a, actually a plus b minus a times alpha, for example. Notice that I didn't really need, hold on, what the, yes, t. See? Oh, you still need the copy, for example. Because num, I think a big int also is included in num. But essentially, you notice right now that although I use plus minus times, like num already includes all of that stuff that I need, other than copy. But I don't really need copy. You could even say clone here, and here where we have the problem, you could just say clone. So this lerp would also work with non-copy types, I think. Or oh yeah, it's actually moved not here, it's moved here. But here, since we don't need that element anymore, since we're moving it, we're just gonna consume it here. Here though, we're gonna need to clone it because we still want the value to exist. But anyways, so there you go. So right now I didn't have to implement add, implement minus, implement times, implement all that stupid stuff. It's already included in num. So if you just want dirty, real quick numbers stuff, there you go. And yeah, I think that's essentially it. I don't think I have anything else to cover at this point. There's still a lot of crazy stuff right out there, but I think I've covered the stuff that you need to go on further and like just learn yourself at that point. The hardest, I think, is the start, the beginning. But yeah, that's pretty much it for this live stream, and thank you for watching, and see you later. Goodbye, everyone.